So today we will move on and do some actual theory on robotics. You see the title is Mathematical Background, still basic things, trying to understand the concepts that we use for robotics, more specifically coordinate systems, vectors, transformations, and we're going to use this through the whole semester. But before we dive into the theory, I want to present you a little bit the big picture of what we're trying to do. So we talked last week in the introduction that we will discover different types of robots. And yes, we want to have robots that do fancy, nice things. But how do we get there? We need to go backwards and understand what elements do we need in order to develop great robots. So in order to have great robots, we need to be able to control them somehow. So that's a concept that we learn, right? We have a device, the robot, but in order for it to do useful things, we need to be able to control it. In order to control the robot, we need to understand its dynamics. All right, a robot can see it like a process based on what you've seen in previous courses like system theory. And in order to develop a controller for this process, we need to understand the process, the dynamics of the process, like how does it behave. In order to understand the dynamics, we need to understand three aspects. How do we report its position, or how do we measure position and orientation? How do we describe its velocities? And how do we do these things in the inverse side as well? Right? In order to understand these three things, we need to talk about kinematics. And to start talking about kinematics, we need to talk about transformations, which is what we'll do today. So we'll start from the left, and slowly during the semester, we're going to build and reach the last part, right? So every week, I'll bring this scheme up and show you what was the progress and how we're going, so that you understand, like, okay, why are we talking about coordinate frames right now? Yeah, because we need it for kinematics. All right, any moment you have a question, raise your hand, just feel free to interrupt. So more specifically, what we'll see today is talk about what is a coordinate system or coordinate frame. Probably you've seen it. You have a question?
Would it be possible to also have access to the materials on Teams?
The slides?
Yeah.
Yes. I put last week's slides, I think. I plan to do it every week.
What would be today's slide?
Now or afterwards?
Not this one, not now, but for future.
I usually put them right after the lecture.
Okay.
But I can put them right before the lecture, if I remember. Okay, but you will have them today. If I forget to put them, please remind me, because we took 1 hour. All right, so we'll talk about what is a coordinate system or coordinate frame. For sure you talked about this, I don't know, in high school. We'll talk about the rules of the right hand. How do we describe vectors in 3 dimensions? And then how we'll define this notion of transformation matrices. And then one step further, the homogeneous transformations, right? All right, so what is a coordinate frame, coordinate system? How would you describe it before I put it on the screen?
Set of indices.
Sorry, a set of indices? Represent the point in space. All right.
I mean, if you know how many centimeters the room has, you can use the measurements of every point in this room to give a coordinate.
All right. So a coordinate is something you give to a point, right?
Yeah.
From what you say. Good. But the coordinate system is or frame.
A system that
Go ahead. It's a reference frame, right? Okay. So it's when we say a reference, it's the entity, let's say, that we use to describe the position of points. There's a reference, right? So it's basically a tool. Let's call it a mathematical tool or geometrical tool that allows us to describe the position of points or objects in space using numbers, right? So it's inverse of what you were saying. We have points in space and we use a system, coordinate system or coordinate frame that to describe that position with reference to something. Coordinate systems have different axes, and the number of axes is equal to the number of dimensions in the space that we're talking about. Right? We can have one-dimensional space, two-dimensional, three-dimensional, 50-dimensional. I don't know. We're not going to go into that. Up to 3 dimensions in this course. Right? So we're talking about axes. Right? What are the properties? The axes have to be perpendicular to each other. Right? Each axis perpendicular to all the others. The length of the axis we consider to have length of 1 unit. Right? That's arbitrary, but yeah. Each point has a number of coordinates which is equal to the number of axes. So when we use a coordinate system to describe a point, it will have the same number of coordinates as the axis of the system. And nothing stops us from having multiple coordinate systems in the same place, in the same space, right? Let's see, again, very basic things. Let's talk about, I don't know, different dimensions. In one dimension, basically, a coordinate system would be just a line, right? And then we can measure things, how far away they are from the origin of that line, right? If we have one dimension, okay? In 2 dimensions, that you probably have seen before, we have a surface, right? And then we have 2 axes perpendicular to each other. Typically, we use X and Y for names, but it can be anything. And then each point can be anywhere on the surface, and it will have basically 2 coordinates. And what are those coordinates in this case? All right, let's say we have point P, which has coordinates 1 and 2. What do these numbers represent? What is 1? What is 2? What does it tell us, these numbers? The distance from the origin, all right, but the distance from the origin is, we have one distance, right? Why do we have 2 numbers? Somebody said? The distance from the axis, okay. So in this case, what would be this 1? What distance? Yeah, the distance basically along the first axis. In this case, we consider x. So it's basically this distance. So yeah, you can say it's the distance from the y-axis, right? While the second number would be the distance along the second axis, or the distance of the point from the first axis. Okay. Along the first axis is more accurate. Okay, in 2 dimensions it's the same thing, but in 3 dimensions we'll see it's different. All right, and we can have different points with different coordinates. Here we see like 3 points. P has coordinates 1 and 2. Q has 2 and 1. R has -2, -3. Right. So it can be negative, it can be positive, whatever. Simple stuff so far, right? All right. As I said, nothing stops us with having more coordinate systems describing the same space. All right, so here we have 2 examples. We have the red frame and the blue frame. And basically the same point, as you see, has the same point has different coordinates in different frames. We have the red P there, which is the coordinates of point P in the red frame or red system, and we have the blue coordinates, which is the coordinates in the blue system. Right? Same point but different coordinates because we describe it in different frames. Right? Here we see an example where the 2 frames are just translated relative to each other, but they can be also rotated. They can be rotated and translated. They can be anything, right? As long as they are on the same space, so basically in this case on the same surface, we can use them to describe the same points. All right? Easy stuff so far. In 3 dimensions, we extrapolate and we use, I don't know, one more coordinate, because we have 3 dimensions. We're going to have 3 axes. So typically we call them x, y, and z. All right, and each point will have 3 coordinates. The distance along the x-axis, so in this direction, the distance along the y-axis, and the distance along the z-axis. The condition is that, as I said earlier, for any coordinate frame, all the axes have to be perpendicular to each other. So x is perpendicular to y and z, y is perpendicular to x and z, and so on. Right? Again, we can have multiple frames describing the same points and so on. Now, first thing that we should learn, maybe you heard it before, maybe not, is what we call the rule of the right hand. In 3 dimensions, we have to be careful about how we assign the axes. Okay, which one is the first, the second, the third axis, right? And they have to respect. That's a convention we use to follow the rule of the right hand, which basically gives us the direction of the axis according to this rule. Okay, and it goes as this. Like, if my thumb is pointing towards the x axis, the index finger towards the y, then the middle finger will show me where is the positive z direction, right? So we need to follow this convention. A second convention hidden here a bit is the colors that we use. Typically in robotics we use red for x, green for y, and blue for z. That's to make things easier to visually understand immediately what axis is where, right? And you can see them here as well in 3D printed version. I'll use this during the course and the labs. We have this red, green, and blue, and if I put them correctly, I have the x-axis on the thumb pointing towards the x, the index finger pointing towards the y, and then the middle finger pointing towards the z, right? All right, I think they're all like this. All right, good. So here in the previous example, I had just one point. But since we're going to have to deal with multiple coordinate frames or coordinate systems, I need a notation to explain the coordinates of a point on which frame they are expressed in, right? So here we see that we call this P0 because these coordinates are with respect to frame 0, right? I can give names to frames just to make things clearer. Right, and let's say the coordinates of this point in frame 0 would be P0, right? We typically write this in this vector format, right? Maybe you remember from math, where I have the square brackets and the 3 numbers would be the 3 coordinates, right? So on the first position would be the distance along the x-axis, the distance along the y-axis, and the distance along the z-axis. Okay. We talk about points in robotics, but we talk more about vectors. But it's kind of the same thing, right? You've heard about the notion of vector, I guess. It's basically like an arrow which shows the direction. So how do we describe a vector in a coordinate frame? We mainly care about the end position of the vector, right? The tip of the vector, right? What we see here. We consider the other side of the vector, like the origin of the vector, to be at the origin of the frame. Right? So in that case, a vector is described in the same way as the coordinates of its endpoint. Right? Good. Now, if we have 2 vectors we want to talk about, we can group them together in a matrix or an array. Right? I have again the square brackets, and I have 2 columns. Each column is about one of the 2 vectors. Right? So here I have v1 with respect to 0, so this would be v1, 0. It has some coordinates, and then these numbers here would appear as a column. All right, and then I have v2, 0, some other coordinates. The coordinates of this point would be this column here. All right, and where I want to reach is basically the case where I have 3 vectors, and we'll see immediately why, where again I can expand to the number of columns, right? We saw that basically a coordinate system or a coordinate frame is 3 axes or 3 vectors, right? That's why we want to have a notation for writing down the position of 3 vectors, right? So that's how we do it, using a 3 by 3 matrix, right? Where each column represents the coordinates of the tip of each one of the vectors. Okay? Simple stuff, I hope. Let's see an example. Let's say we have this coordinate frame, the black one. Okay, and in this frame we're trying to describe the position of these 3 vectors. And it happens that these 3 vectors are aligned with the 3 axes, right? And they have length 1. So in that case, this vector here, v0, v1, 0, would have coordinates 1, that's the distance along the x-axis, and 0, 0, because it doesn't have any distance along the other 2 axes. v2 would have 0, 1, 0, and v3 will have 0, 0, 1, right? If I write these 3 vectors using this notation, what will I end up with? Let's say I write here v1, 0, next to it v2, 0, and next to it v3, 0. What will I end up with? The I. Why? Because this one will have 1, 0, 0. This one is 0, 1, 0, and then this one will have 0, 0, 1, right? So when you say I, you mean, I guess, the identity matrix. It's called I in programming, but in mathematics is the identity. I because it's I. So basically, what does this tell me? If I have a coordinate frame, a reference frame, the black one, and I have another frame that happens to be identical to this frame, so I basically have this frame, and then I put another frame right with it. Yeah, it shouldn't have happened, but anyway, you can imagine all the axes aligned. Then how I describe the red frame with respect to the black frame is using the identity matrix, because they're basically identical. Okay? Good. So this is the identity matrix. Now things is not always so simple, like we have frames on top of each other. We have things that are moving relative to each other. So let's see, how do we express frames that are rotated and later on translated relative to each other? So robots are about motion, things moving, okay, and one of the elementary ways of moving is through rotations, things rotating relative to each other. Let me try to untangle this. That's going to be tricky. So we see how things rotate. I got 2 strong magnets. And here. So let's say I have a base frame, and I have should be this way. All right. And then I have another frame. So this is my reference frame, and I have another frame that I just want to express. And then I can have like rotations. So one frame rotating relative to each other. I'm not putting them very close because they snap, but you can imagine like this being here and being rotated relative to the first frame. either like this, or around this axis, or around this axis, right? Oops. I can express these rotations using this kind of matrices, right? I have a different matrix for rotation around each axis. So here, for instance, we have the rotation around the x-axis. I have the rotation around the y and around the z, right? Here, what do we see? What did we say that these 9 numbers represent? Right? The first column would be the coordinates of the first axis of my frame. Okay. The second one would be the second axis. The third column will be the third axis, right? And let's say, for convention, again, the first one is the red one, then it's the green one, then it's the blue one. So x, y, and z, right? So if I talk about rotation around the x-axis, or around the red axis, right? I'm talking about the rotation like this, right? Rotation around the x-axis, right? What do I see? Are the coordinates of the first vector changing? No, they don't depend on this rotation, right? Because the red axis, this is less stable than I thought. I put it the other way around. Because the red axis does not change relative to the reference frame, right? Right, but the other two axes change, and how do they change? They follow basically trigonometry, cosinus, and sinus. So let's take the second axis, right? When theta is 0, so I have no rotation. Oops. Right? What happens here? I have 0. Cosinus of 0 is 1. Sinus of 0 is 0. So I'll have 0, 1, 0. Right? So I have the same coordinates for the one that rotates as the original one. And the last column will be for theta 0, it will be 0, 0, 1. Right? So I will have again the identity matrix, but when I rotate, let's say by 90 degrees, right? What will I have? If theta is 90, 0 cosinus of 90 will be, let's write it down so it's clear. So r x 90, I'll have 1, 0, 0, and then here I'll have 0 cosinus of 90, 0, sinus of 90, 1. All right, so let's have a look at this. So if I rotate around the x, let's put this here because it sticks. If I rotate around x by 90 degrees, what are the coordinates of the new y-axis with respect to the old frame, to the reference frame? 0, 0, 1. So basically the coordinates of this point here has 0 on x, 0 on y, and 1 on z, right? You see it? And what happens with the last column when theta is 0, is 90, Sinus of 90, 1. With the minus there, it's going to be minus 1. Cosinus of 90, 0. Right, so this will be the coordinates of the rotated z with respect to the reference frame. So I will have 0 on x, right, it's here, minus 1 on y, right, because it's on the opposite direction, and 0 on z, right, the coordinates of this point. Okay? So that's why this matrix here represents the coordinates. You can think of it like this, the coordinates of the tips of these vectors for a rotation around x. I showed it just for 90 degrees, but it works for any rotation, obviously, because these points will go around the circle, basically. Okay? Same for rotation around y. Now I have this kind of rotation, so if I can do this actually. Now I have this kind of rotation, right? like this. So let's see how does this work out. So if I have a rotation around y by 90 degrees, first thing to observe is that the second column doesn't change. The second column represents the coordinates of the green axis, right? The second axis. And obviously the coordinates of this axis don't change for rotation around its own axis, right? Good. So this will always be 0, 1, 0. What happens to the x? If I rotate, let's say, by 90 degrees, what values will I have there? Cosinus of 90, 0, 0, minus 1. And that's what we see when we rotate by 90 degrees. This one will go in the negative z. So it will have 0 on x, 0 on y, and minus 1 on z, right? And what will happen with the z? It will be 1, 0, 0, right? So now the z has the same direction as the old x. That's why it has 1 on x, 0 on y, and on z, right? Same idea when rotating around z, right? There we see that the last column doesn't change because the z, if I rotate around z, the coordinates of the point, of the tip point of the z will not change. Okay, but the other ones will follow the, okay. Okay, good. So here we see a bit of visualization of these three rotations, if we're talking about points or whatever. Yes. Now, we will see that these transformation matrices represent basically two things. It's, how do we interpret them? We saw here that using this notation, we describe the coordinate frame. Okay, it's the coordinates of a reference frame with respect to another frame. Okay, and these coordinates can change by, rotating things around. But it's also these matrices represent the action of transforming a frame around a certain axis. All right, so this one represents the already transformed frame, but I can use it to also move another frame or rotate another frame around x by 90 degrees. Okay, how do I do this? If I have a reference frame, if I have, a coordinate frame expressed in a reference frame, so let's say this V0, which happens to be aligned with the reference frame, so it has basically the identity matrix. I can rotate it around the x-axis by some degrees by multiplying from, we'll see left, right immediately, but by multiplying that original frame, all right, by a transformation matrix. So if I do this operation, if I do this multiplication, it's as if I'm rotating that frame, all right? Now, why do I say that these matrices represent both the action of transforming, of rotating in this case, but also the rotated frame? And we can see in this example, what happens if I take, let's say, this transformation, rotation around x by 90 degrees, and I multiply it with this V0, which would be this one, right? What is V0? Is the identity matrix, right? Am I doing anything by multiplying a matrix with the identity matrix? Nothing, right? So in that sense, this can be seen as the transform matrix, because if I multiply this matrix with the identity, I will get back this matrix. So this is the transformed matrix, but it's also the action of transforming because I can multiply it with the identity matrix, right? We can actually multiply it with any matrix, right? It doesn't have to be the identity matrix here. So basically, after I rotated this identity matrix to some orientation around x, nothing stops me from multiplying another transformation on it, right? So I can, let's say, in this case, start from the identity matrix, V0, rotate around x by an angle theta. So I don't know, something like this. So this is my, this is my initial frame, and ignore the translation for now. Let's say I rotate around x. Okay, and then I do another rotation around y. So let's say, will this work? No, it won't work. And maybe let's do it in steps so it's more clear, since we have the frames. So we first did the rotation around x and then around z. Forget the translation for now. If I put them too close, they will get. But yeah, what I do between this one and this one is I rotate around x, right, by 90 degrees. And then what I do between this one and this one is I rotate around z. Around the green axis, so y, right? And I can do this by subsequently multiplying with this transformation, right? So I start with identity, let's say, I rotate around some axis, and then I can rotate around another axis. I can do as many rotations as I want, right? Because these are all 3 by 3 matrices, what will be the result of its multiplication? So let's say I have this frame here, which is a 3 by 3 matrix, and this one here, which is a 3 by 3 matrix. What will be the result? Another 3 by 3 matrix, right? So I can keep on multiplying with these 3 by 3 matrices as much as I want, and I will keep on having as a result a 3 by 3 matrix which represents a coordinate frame. Okay? Good. And what we can show, we will not explicitly show it now, but the idea is that no matter the orientation between two frames, I can always express it using these elementary transformations, which is simple rotations around x, y, or z, each one of the 3 axes. All right? Ignore the translations for now. We'll talk about translations in a second. All right, so some more visualizations here, how these rotations look like. So at the top we have a rotation around the red axis, x, there around the y axis, here around the z. I didn't have these frames in the past, so the visualizations were maybe more useful, but I hope these are helpful too. All right, clear so far? Good.
The order of multiplication method?
Sorry?
Does the order of multiplication method?
Yes, it does. And we'll see about this in 10 slides or something. It does. Right, good. Before we see the order of multiplication, let's put in the game also translations. Because we only talked about frames rotating, but we might have also frames, translating relative to each other. In order to talk about translations, we need to expand these matrices from 3 by 3 matrices to 4 by 4 matrices. So this is what we call the homogeneous transformation matrices. Okay. How do we expand to 4 by 4? We keep the orientation matrix or rotation matrix on the top left corner of the new matrix, and we add a new column and a new row. All right. So this 3 by 3 is the same as we saw before, representing orientation, and we add a new column with 3 numbers. This 3 by 1 vector, 3 rows, 1 column, which represents change in position, or translation, right? And then the bottom row, we always fill it in with 0, 0, 0, and 1. Okay? Good. And now we can talk about homogeneous translations, right, which have the same logic as these rotation transformations. Okay? And the way we move things around, or we express movement, is again we use elementary translations along the three axes. So along the x-axis, the y and z, and basically the form of these matrices is like this. So the orientation matrix remains identity, since we're just translating, right? And we change one of these three numbers. The first one, if we have translation on the red axis, the first axis, the second number on the second axis, and the third one on the third axis. As I said, typically first, second, and third is x, y, and z. Right? We can use the same matrix form for rotations as well. If we have pure rotations, so now we don't have any translations, then the translation part of the matrix will remain to 0. Right? And in here we will have the same form as we had before for the rotation around x, y, and z. Right? If you see, it's the same numbers. Okay? Right. Now, in order to move things around, we also need to, so here we said that we have a coordinate frame represented by a 3 by 3 matrix multiplied by a 3 by 3 matrix. Okay, if we expand to a 4 by 4 matrix for transformations, then we need to also expand to 4 by 4 matrix for the coordinate frame, right? So we define a broader definition for this coordinate frame, right, as a 4 by 4 matrix where basically we have again the identity matrix for the frame placed at the same position and orientation as the reference frame. And here we have the orientation part expressing, okay, how the three vectors are, the coordinates of the three vectors with respect to the reference frame. And these three numbers would be the position of the origin of the new frame with respect to the reference frame. So just to make it more clear, if I have two frames, what is the origin? The origin is basically where the magnet is for these frames, all right? So what will I have in these three numbers? It would be the position of the reference frame I'm describing there with respect to the coordinate frame with respect to the reference frame. Okay? We'll see with examples, maybe it will become even more clear. All right? But yeah, these three numbers represent the position of the origin of the frame I'm describing with respect to the reference frame. Okay? And it can be very strong magnets. Can be, I don't know, anywhere in space. It has coordinates. Anything else here? No. Is this part clear with the 4 by 4 matrix? Good. I'm taking it slowly, so it's clear. Right. Now, let's go back to what you asked. Right. When I transform things, I say I multiply things. And since we have square matrices, 4 by 4s from now on, I can multiply either way. Right? I can have a coordinate frame V, I don't know, A, and I can apply transformation on it either like this, by 90 degrees, or I can do, I don't know, this thing. Is this the same? Will it give us the same result? Yes, no, maybe. By
maybe change scenarios.
sorry?
Maybe scenarios?
Maybe certain scenarios, yes. But since these are matrices, right, what you know from algebra is that in general, matrix multiplication is not commutative, right? So in general, AB is not equal to BA when we multiply matrices. Sometimes it is, depends on some conditions, we'll see, but we should in general consider that it's not. All right. But we are allowed to do both of these, right? Mathematically, I can do both operations. And also when transforming frames, we can do this. It's just that it has a slightly different meaning. All right, so let's try to see this. So when I have a frame that I'm trying to rotate or transform anyway, something that we really need to understand is that a frame is always expressed with another, with respect to another frame, right? So basically we'll have two frames. Let's put it like this. And let's say this is the reference frame. Let me even write it. And this is, I don't know, frame A in this case, right? When I multiply from the left, so I have this frame A, so I have this VA, okay, which is frame A expressed with respect to the reference frame, okay, VA, or maybe let's better call it VA with respect to reference, okay. When I multiply from the left, I basically apply a transformation with respect to the axis of the reference frame. What does that mean? Let's say, let's start with a translation first. Let me, oops, sorry, because that's a bit easier. Let's say I have this reference, V reference A, and I do a translation on X by, I don't know, 1 unit. What will happen then? I will basically translate along the reference X, right? So I will do something like this. I have to remove it, but I will do something like this, okay? I will not stick it. If I do a translation on Z, then I will do something like this, right? Good. What about rotations? If I rotate here around X, what will I do? I will rotate around which X, because I multiply from the left, around the reference X. So I will do basically something like this. It's as if I have a rope, you know, connected to the origin here, and then doing this thing, this movement, okay? This is my axis of rotation. If I do a rotation around Z, okay, I will do basically something like this, right? See, the orientation also changes, right? Because it's as if, I don't know, this axis is connected here and it will rotate as it rotates around the axis. It's like, I don't know, a door opening or something. Okay? Good. This is what we call absolute transformation, or anyway, multiplication from the left. And this is what you see here as well. I have a, where is it? Here you are. A reference, a coordinate frame with the thick one with respect to the thin one. And if I multiply from the left, I will rotate as I explained there. Okay? Now what happens if I multiply from the right? So I have the same reference frame, I have the same coordinate frame A here, and now I do a translation on X by 1 unit, and I multiply this from the right. Now I don't translate along the reference X-axis, I translate along its own axis. So I will do basically this. Okay? You see also x is pointing towards you from the reference. This one points to the right. So this goes like this. Okay? If I do a translation on z, I will get out of the board and will come there. Right? Good. If I do a rotation around z, then again I don't rotate around the reference z, but I rotate around its own z. So I do something like this. Sorry for the... So I do something like this. Okay, if I rotate around, I don't know what's easier now. If I rotate around x, I will do basically this thing. Around y, I will do this, right? Not this. Clear? That's the difference between multiplying from the left and multiplying from the right. But what should be clear is that VREF, this 4x4 matrix, is always described with respect to a reference frame. Because we said that these numbers that appear here are coordinates of the points, of the vectors, and of the origin, right? So if we have coordinates, they must be expressed with respect to a reference frame. So there is always a reference frame. And that's why if I multiply from the left, I translate along the axis of the reference frame. If I multiply from the right, I transform around its own frame. Okay, so here we see both of these combined. So I have a V0 somewhere arbitrarily oriented, and if I multiply from the left, it does a rotation around x, it does this motion. If I multiply from the right, it rotates along its own axis. What we saw here as well. Okay? Same for translation. Okay, this one, if you see, translates along this direction. This one translates along this direction. Small difference. Any questions so far? No? All clear? Shall we take a break?